Hi, I'm Mrs McTaggart. In this video we're going to be looking at the third video in a series of lessons on similar shapes. And this one we're going to look at what happens when we start talking about the area of similar shapes. So before I start, I always use this argument I once had with my husband back when we were fighting over what size shed to get. We used to have a 6x4 shed in our garden, and I had suggested getting a 8x12 shed. So you'll notice the measurements from this is 6 feet by 4 feet and 8 feet by 12 feet, because sheds are measured in feet. It really doesn't matter whether it's feet, inches, metres, centimetres, the connection with the area is still the same. So our first shed had a floor space of 6 feet by 4 feet, and the second one had a floor space of 8 feet by 12 feet. And I had argued with my husband, right, well, I mean, it's double the size and dimensions, so you've quadrupled your area or your storage space. And he went, no, I haven't. And I said, yes, you have. And he said, no, but if you've doubled the lengths, you've doubled the area. And I was like, well, wait a minute, let's prove this is false. So first thing we're going to look at is what is the scale length, the scale factor for the lengths here. Well, both my dimensions have doubled. I know the shed has kind of rotated a wee bit, but 6 has been doubled to 12 and 4 has been doubled by 8. So essentially this shed is double the length of the previous one. So I would say the scale factor, or the length scale factor in this case, I'm going to call it LSF for short, length scale factor is 2, because I've doubled the dimensions. But did I double the area in this shed? So that's the question. This is what the argument was about. And I said, well, let's look at the area of the bases. So the area of the first shed, which is 6 by 4, has an area of 24 square feet. And the bigger shed, which has a base of 8 by 12, oh, I've done that the wrong way, 8 by 12, well, 8 times 12 is 96. So that would be 96 square feet. And I said, well, we've doubled the length, but we've certainly not doubled the area, because if we're doubling the area, I'd expect the new area to be 48. So what has actually happened? What have I times by there? 24 times what number gives us 96? It is actually 4. 24 times 4 is 96. So doubling the length quadruples the area. So there must be a way to mathematically solve this, depending on whether I'm tripling the lengths or quadrupling the lengths. So let's try and explain this very simply using some squares. So if you look at my first shape, I have got one small square and with sides of 1. And I have doubled the length, so I now have sides of 2. But my area has gone from 1 to 4 by counting the boxes. So my length scale factor is 2 because I've doubled the length. Area A has got an area of 1, area B has an area of 4. So I've actually done my the lengths times 4 to get the area. Let's look at my second one. The small one is 1 by 1, so it has an area of 1. The big one is 3 by 3, so it has an area of 9. So the scale factor this time is 3, but the area has gone from 1 to 9. And before, the area went from 1 to 4. So can you spot the connection? When I doubled the length, I ended up timesing by 4. And when I doubled the length and when I tripled the length, I ended up timesing by 9. Can you spot the connection? It's something to do with square numbers. 2 squared times 1 gives me 4. 3 squared times 1 gives me 9. So in actual fact, once you've got your scale factor, you have to square it. And let's just think, if I drew another square that was 4 by 4, that would be me quadrupling the areas, and the area would go from 1 to 16. 4 squared times 1 is 16. So this is the bit where you have to start copying down as your note in class. So if two shapes are mathematically similar, to find a missing area in another shape, you simply multiply by the scale factor squared. So I have this little formula here. I never ever write this out. I just write it at the top of the page and then that's it. So if I want to find an area of a new shape, it's whatever my scale factor is, I square it and I times it by the old area. And then your scale factor is the same as normal as before. It's either an enlargement scale factor or a reduction scale factor. So let's have a look at some examples. Now, as far as possible, I try to do these all non-calculated, okay? So we are going from a small to a big one. So the first thing you do is you get your enlargement scale factor, so I'm calling it ESF for short. And because we're going to enlargement, we put the big number over the small number. So we compare the numbers that match up. So we do 12 over 3 which is just 4. And I'm sure you could probably just look at that and say, oh, she's quadrupled the lengths. But it's not always easy numbers, so I'm going to stick with this method, big over small. So my enlargement scale factor is 4. That is my length scale factor. Then to get the new area, so I'm going to write area equals, it's your scale factor squared times the old area, which was 5. So the sum is 16 times 5, which is 80. So the area of that larger rectangle would be 80 square centimetres. Okay, let's have a look at another one. Okay, this time I'm going from a big triangle to a small one, so I'm doing a reduction. So my reduction scale factor is small over big. So it'd be 2 over 8, which simplifies down to 1/4. And again, you might be able to just look at that and say, oh, she's divided before, so which is essentially the same as quartering. So to get the new area, we do our scale factor squared times the old area. Now, when you're squaring a fraction, if this was a calculator, I would just go straight into my calculator and type in 1/4 squared, which would be 0.25 squared times 320, and 0.25 squared would be 0.625 times 300. But you could do it all in one go, but we can do this non-calculator. If you square the top number, you get 1. Square the bottom number, you get 16. Times that by 320. And then good old divide by the bottom times by the top works here, because 32 can divide by 16, so that actually cancels out and that becomes 20. So I'm left with an answer of 20 square centimetres. So again, you could use a calculator here, but where possible I'm going to do it without, okay, because this could be in a non-calculated paper and it's a skill we really need to work on. Okay, my third example. These two pictures are mathematically similar, and you'll find that whenever you buy paintings or when you get a photograph, they are all mathematically similar, just either shrunken down or enlarged, but the dimensions are similar. Otherwise the picture would distort as you stretched it or altered the images. I mean, you'll know yourself if you've ever had to stretch an image on a Word document. If you don't alter it exactly as an enlargement, it gets a wee bit weird looking. But this, what I like about this one is it doesn't talk about area. It just says the cost of each picture is proportional to its area. And it has also told you that it is mathematically similar. So this is your clue to do this method. They have told us the cost of the large picture is £13.75. So the cost is dependent on its area. That's what it's basically telling me here. So we just proceed as normal. But at the end, it's not our scale factor squared times old area, it's cost we put in. So if we're looking for the area of the smaller picture, it's reduction scale factor. So small over big, so 60 over 100, which is your 20 times table, gives you 3 over 5. And then we would say that the new cost is 3 over 5 squared times 13.75. And this would definitely be a calculator paper. So if you type that into your calculator, it gives you an answer of 4.95. So the cost of this smaller picture would be £4.95. Now I've got one more example to show you. This is again, I'm sure this is from a past paper. This one we have the two triangles set within each other, which you've maybe seen in a previous video if you watched video 2. These triangles are mathematically similar, it tells you in the question, and they're mathematically similar because they both share this common angle here at angle R. It's told us the area of QRT, which is this red bit. They've told us the area of this little bit is 400, and they want the area of PQTS, which is this kind of quadrilateral trapezium shape that's going on in here. So, I mean, my trick with this one is always to draw the two triangles out. So I'm going to draw the large triangle first, and then I'm going to draw the smaller triangle. So I know that the smaller one has 24 and an area of 400. And the bigger one has a height of 30 and we're after its area. Now there's no way to get this little area here, which is denoted by the blue bit of the flag, but I can get the area of the large triangle first and then we'll subtract, because the area of this little shape here that we're after is just the big blue triangle with the red triangle cut away. So we are looking for basically the larger area, so this is an enlargement scale factor. So it will be big over small, so 30 over 24. which simplifies down using your 6 times table to 5/4. So my new area would be 5/4 all squared times the old area, which was 400. I think this is a calculator one again. So 5 divided by 4, if you square it and times it by 400 on your calculator, gives you 625. So that means the area of this whole triangle here is 625. We're going to subtract 400 to get the area of PQTS. So I'm just going to write the PQTS equals 625, take away 400, which is obviously 225 square centimetres. Okay. And I'm just looking at this one wondering, could it be on calculator? I haven't written down what paper it came from. But if it was on calculator, let's humour maybe a second and see if we can do it. If I square the 5, that would give me 25 on the top. 4 squared would be 16 times 400. Now, I know that 4 will go into 16 and the 4. So if I divide this by 4, I'm left with 4. If I divide that by 4, I'm left with 100. So actually, I'm left with 2500 divided by 4. And then if you half it and half it, you do get 625. So yeah, possibly that could have been a non-calculator question there as well. So I have exhausted all the different styles of area questions I can come up with. This is a point in the video if you wanted to try some. Here you go, you could pause it and try these ones. They are all non-calculator. I checked the numbers myself. I just think it's more of a challenge doing it without a calculator, and it just prepares you for what to do if it does appear in a paper one anyway. And then if you unpause the video, you will see your answers are all written in the blue there. I hope this has helped. Thanks for watching.